Hello everyone. In the previous lecture, we saw some applications based on Gauss law. In this lecture, we will continue to apply Gauss law in few more cases. The first case here is to find electric field due to a thin spherical shell. A thin spherical shell, which is a conductor, would basically mean that the charges are present only on its surface. Let's assume that the charge is distributed uniformly over its surface, and here we will assume that the charge is a positive charge. Let its radius be some capital R. So capital R is the radius of this thin spherical shell. Our aim is to find electric field at a given point. Let's assume that we need to find electric field at some point here. At some point here, we need to find the electric field. Let that point be P, and let the distance between the center to this point to be R. So we need to find the electric field at this point P. In this case, we'll define surface charge density called as sigma, and sigma is given as charge by area for the entire sphere. Entire sphere, sigma would be, let the charge be capital Q. So let capital Q be present over the entire sphere. So capital Q by area would be 4 pi into capital R square. This is a constant, and recall from here that we can write charge as sigma into area. Now since the point is P, we saw in the previous class that we need to choose a Gaussian surface such that that Gaussian surface passes through this point P. As seen in the previous lecture, the most sensible surface would be a sphere again. So let's draw a sphere around this spherical shell such that that sphere should pass through the point P. As seen here, drawn a sphere. Now let's use Gauss law, or let's find flux for this sphere first. So the total electric flux would be given as integral of E into dA into cos theta. Now if we take any small area, for example, if we take a small area somewhere here, the small area, and for this area the area vector would be normal to that small elemental area, we call that as dA. So dA is normal to this sphere, and also electric field will go out like this. So field will go out like this only. So that in this case, what we find is, we find that the electric field and area vector are in the same direction. If you take some other small area here, a small area on the sphere, even for this, the area vector would be normal to this part. We saw this in the theory part. So the area vector would be normal to it. It's normal to this part. We call it as dA. Similarly, the electric field from here would also be going out radial outwards. So even the field also goes out like this only. So what we find here is, we find that the electric field and area vector are in the same direction. So we can take up similar arguments everywhere. If we take any small part anywhere on the sphere, for all the small areas, the angle between the electric field and the small area vector would be 0. Therefore, since theta is 0 for all the elemental areas and electric field, cos 0 is equal to 1. Therefore, the flux is equal to, and do remember, the distance from the sphere to the Gaussian surface, this one is the Gaussian surface is always same. That would mean that the electric field would be same at all the points on the Gaussian surface, because of which this E, which becomes a constant. So E comes out, and what remains would be, it's a closed integral, so it would be into dA, and dA would mean adding all the small area elements. If we add all the small area elements, then what we get would be the total surface area of the sphere. Therefore, flux from here, flux is equal to E into 4 pi into small r, because for the Gaussian surface the radius is small r, so into small r square. We'll call this as 1. Next is, by using Gauss law, do remember we're following the same method only. In all the cases, we are first finding the flux by definition of flux, and then we are finding flux using Gauss law and equating both of them. Here we have found out what is the flux by using definition of flux. Now we'll use Gauss law. So from Gauss law or Gauss theorem, we know that the total electric flux is equal to the charge enclosed by epsilon naught. In this case, this Gaussian surface encloses the whole charge capital Q. Therefore, what we get from here would be capital Q by epsilon naught. We call it as 2. Let's equate 1 and 2. So, if we equate 1 and 2, then what we get is E into 4 pi r square is equal to capital Q by epsilon naught, or from here E is equal to capital Q by 4 pi epsilon naught into 1 by r square. So this is the electric field at a point outside the sphere. Now what we do here is, in vector form, you can say vector E is equal to capital Q 4 pi epsilon naught 1 by r square into r cap, because it goes out radially. And do remember, this is a point outside sphere. We'll just write it here. So we'll take a case 1 where it is a point outside the sphere, or shell in this case, outside the spherical shell. That's the first case. Now observe carefully here. This expression, what we derived here, is similar to the electric field due to a point charge also, because recall, for a point charge, electric field was given as 1 by 4 pi epsilon naught Q by 1 by r square. This is the expression for electric field due to a point charge. So these two are similar form only, in fact the same value. That means that for any point outside the spherical shell, any point outside it, this spherical shell behaves as if a point charge. It's actually a theorem. It's called a shell theorem. So by shell theorem, this is called a shell theorem. That's the name of it. So what it means is that for any points outside the spherical shell, the shell behaves as if it's like a point charge, which means we can replace this arrangement by a point charge of charge capital Q, and the point P is somewhere here, such that the distance between this point to this, to the center of it, basically to this point P, would be R. So it's equivalent of a point charge. In terms of sigma, we know what sigma was. Sigma was equal to 2 by 4 pi r square. If we put it back here in terms of sigma, then we get E is equal to Q by 4 pi becomes sigma into capital R square. So sigma into capital R square by epsilon naught into small r square into r cap. So this is the form in terms of sigma. Take second case where the point, when I say point, it means it is a point where we need to find the electric field. Point is on the shell. If the point is on the shell, then what we get is, from here we get, this is what we actually got. So if you rewrite this, E is equal to capital Q by 4 pi epsilon naught into r square. Here small r becomes equal to capital R because small r is general point. It's a variable. So when we want to find the field or charge itself on the shell itself, then small r in this case becomes equal to capital R. So in that case, what we get here is, in fact, it's very close to capital R, not exactly. So technically you should write it tending to capital R because on the shell the value is not defined. But most books will write small r is equal to capital R. The actual meaning is it's very close to it but not on it. So in that case, what we get here is, mathematically, this E is equal to capital Q by 4 pi epsilon naught into capital R square. Look at this. Now in this spherical shell, capital Q is a constant, 4 pi epsilon naught a constant, and even R is a constant because R is the radius of the spherical shell. So this value would be a constant. So on the surface, or very close to the surface, the value of E would be a constant. And we'll take a third point where we need to find the value of electric field somewhere inside the spherical shell. So the third case is, point is inside the spherical shell. So we need to find what is electric field for this point inside the shell. Again, if you want, you can redraw the diagram. We can just redraw the shell part. So let the charge capital Q be present or be distributed over the entire spherical shell. Now do remember that the radius of the spherical shell is capital R. Now we want to find, say, the electric field at some point. So we want to find at this point, say I'll call as point A, the distance between center of the spherical shell to this point, let it be some R. We want to find here. Now same as the previous discussions, even here also we can draw a Gaussian surface. So even here we can draw a sphere of radius R. Now here, if you find it, if you use Gauss law, then the total electric flux is equal to charge enclosed by epsilon naught. But here this shell doesn't enclose any charge because the charge is distributed on the surface. So in this case, Q enclosed is 0. Therefore the flux would be equal to 0. If we equate this flux, with the form phi is equal to integral of E into dA into cos theta, if we equate this, then we can infer that electric field should be 0. That's the inference of it. So this means that the electric field is 0 inside the spherical shell. If you plot a graph of electric field versus distance, where we plot the electric field along, we'll call distance along the x-axis, this is r, and the field along the y-axis. So what is seen is, for a point inside the sphere, the field is 0, and the field starts from the point just outside the sphere or very close to the sphere, which is a constant. So if you take a point which indicates its radius, so this would be center of the sphere. When you keep on going from this point O, somewhere we would touch the radius. So at this point the field is a constant, and that value, if you're plotting E on this side, that value is a constant as given here. That would be Q by 4 pi epsilon r square, that's a constant. So this value here is Q by 4 pi epsilon naught into r square, and then from there the field goes as 1 by r square. So the field decreases rapidly, it goes like this. So the variation here is proportional to 1 by r square. This means it is proportional. So meaning of the symbol, it's proportional as given here. It's a curve, it's a falling curve. It goes like this. It falls very rapidly, not a straight line, it's a falling curve. The next case is to find electric field due to a solid sphere. A solid sphere basically means a sphere which has mass everywhere inside the sphere, which means it will have charge everywhere inside the sphere. Let us assume that it is having positive charge. So charge is present everywhere in the sphere. Unlike the previous case, the charge was present only on the surface, not inside. But here the charge is distributed over the entire sphere. So here let its radius be some capital R, and we need to find electric field at 3 more points, same as in the previous case: a point outside the sphere, a point on the sphere, and a point inside the sphere. Before doing it, we'll define a term called as rho. We saw in the previous lectures that rho means volume charge density. So it is given as charge distributed over the entire volume. So from here, charge would be rho into volume. In this case of a sphere, if the total charge is capital Q, so if this charge is distributed over the entire sphere, then from here rho is equal to capital Q. It's a sphere, its volume is given by 4 by 3 pi r cube. But sphere and volume is 4 by 3 pi r cube. So let's begin the derivation. We'll take case 1 for a point outside the sphere. So let that point be somewhere here. Let that point be, say, a point A, such that the distance from the center to the point A, let that be some r. So r here is a variable. So distance from here to here would be r. So we need to find the electric field at this point A. So the best thing is to use Gauss law, and for that we need a Gaussian surface. Again, by common sense, we can tell that the best fit surface here would be a sphere. So we'll draw a sphere around this. As seen here, we have drawn a sphere of radius small r. Again here, we will take few small elemental areas. If we take a small area somewhere here, a small area here, then for this area, it's on the sphere. So for this area, the area vector would be normal to that part. So it will be going out normally. And also, electric field would be going out radially because it is a spherical symmetry. So the field from this will go out like this. So what is seen here is, in this case also, the angle between the electric field and area vector would be 0. Suppose we take the electric field somewhere from here. Imagine that the field goes out from the sphere like this, because the field would be going out radially. So this would be the electric field. Similarly, we take a small area here, small region here. For this area, if its value is dA, for this area also, the area vector would be normal to that point. That will be along dA. So we are saying that by choosing surfaces which are symmetrical to the distribution of charge, Gauss law becomes very easy. Now you should remember that what are the surfaces for given condition. Otherwise, taking something like a cylinder or a cube in this case would make it difficult to integrate. So what is seen here is, at all the points, the angle between the electric field and area vector, which is called as theta, is equal to 0. That would mean that cos 0 is equal to 1. It's same for any area element, whether take it here or here. For all the area elements, the angle between the electric field and the area element would be 0. So the flux from here, which is defined as closed integral of E into dA into cos theta, this term is anyway 1. And also remember that we taken a sphere such a way that the distance between the charged sphere and the Gaussian surface, remember this is the Gaussian surface, imaginary sphere what we draw. So the distance from the charged sphere to the Gaussian surface is always same, which means the electric field in magnitude would be same at every point on the Gaussian surface. That would mean that from this integration E comes out, and what remains is, it will be closed integral of or the dA, because here cos theta is equal to 1. If you add all the small areas, what we get would be the total area. Therefore, electric flux is equal to E into, it is area of the Gaussian sphere, that will be 4 pi into r square. So this is the first equation. Again, same as in the previous discussion, we find the electric flux using the definition of electric flux. Next thing is, we find flux using Gauss law. So using Gauss law or Gauss theorem, we know that the total electric flux is equal to charge enclosed by epsilon naught. Charge enclosed here is a charge enclosed by the Gaussian surface. Now this surface encloses the total charge capital Q. Therefore, this is equal to capital Q by epsilon naught. This is recorded as 2. Let's equate 1 and 2. So from 1 and 2, we find that E into 4 pi r square is equal to Q by epsilon naught. Or from here we can say E is equal to Q by 4 pi epsilon naught. into 1 by r square. So this is the required expression for electric field outside the sphere. In terms of vector equation, you can write capital vector E is equal to q by 4 pi epsilon naught into 1 by r square into some direction they call as r cap, which means it goes out radially. Now, as seen in the previous discussion, even here this form is same as the form for a point charge, because recall that for a point charge electric field was given as q by 4 pi epsilon naught into 1 by r square. Now that means that for any point outside the charged sphere, the charged sphere behaves as if it's like a point object. So remember this fact also. This is what is E. You can also express E in terms of sigma also. Recall what is sigma. Sigma is given as capital Q by 4 by 3 pi r cube. You can express it in this form also. Put it here. Now let's next take a point which is on the sphere. Again from here, if you use on the sphere, that is for a point on the sphere, for a point on the charged sphere, then what we get here is we get small r is equal to capital R. That would mean that E is equal to q by 4 pi epsilon naught into 1 by r square. So this is a form for E for a point on the sphere, or it actually means it is slightly above the sphere, because on the sphere we can't define electric field, but then books write R is equal to capital R, but the actual meaning should have been R tends to capital R, which means it's slightly more than capital R, not exactly capital R. So this is a field for a point on the charged sphere. Now comes an interesting point. For a point inside the charged sphere. So we'll take a point inside the charged sphere. We'll first draw the charged sphere as given here. It has charge everywhere inside it. So let its radius, as defined earlier, be capital R. So from here to here it will be capital R. Now we need to find the electric field at a point inside the sphere. So let that point be A. The point is A. So let that point be A. So the distance between this point A to this be some R. So R is the distance between the center of the sphere to this point where we need to find the electric field. Again here you can use Gaussian surface. So that should be a sphere. So we'll draw a sphere around this point like this. Think of this as a sphere. So this is the point where we should find the electric field. Now the interesting point here is there are some charges which are outside the sphere. So these charges are outside the sphere, and there is some charge inside the sphere. So there is some charge inside the sphere. Now again by Shell theorem, the contribution of electric field at this point is only because of those charges which are present in this sphere. So here this would be the Gaussian surface for us. So the contribution to electric field is not the total charge, rather it is only that charge which is part of this imaginary sphere. we will call it as Q dash. Charge in this region we'll call it as Q dash. Again here, if you use definition of electric flux, so flux is defined as closed integral of E into dA into cos theta. Even from here also the field will go out because there is charge present here. The field goes out like this. So the angle between the small area in the field here would be 0, such that this flux would be E into integral of dA as seen in the earlier cases, that is E into 4 pi r square. So this is the flux inside the point inside the charge sphere, and by Gauss law we know that from, we call this as say 3, from Gauss law we know that the total electric flux is equal to charge enclosed by epsilon naught. So here charge enclosed was called as Q dash by epsilon naught. So let's first find what is Q dash, because Q dash is that charge which contributes to the electric flux. So Q dash is equal to, from definition of rho, we saw rho is equal to charge by lambda, but charge would be rho into volume. So it will be rho into volume, and volume is volume of this region where charge is present, because we're trying to find Q dash the charge only for this region. So that volume would be, even that is a sphere, so that volume is equal to 4 by 3 pi into r cube. That would mean that electric flux is equal to Q dash, which is rho into 4 by 3 pi r cube by epsilon naught, that is equal to rho into 4 by 3 pi r cube by epsilon naught. We call it as 4. Now comparing 3 and 4, because we obtained 3 from definition of flux and 4 from Gauss law. So comparing 3 and 4, E into 4 pi r square is equal to rho into 4 by 3 pi r cube by epsilon naught. From here 4 gets cancelled and pi gets cancelled and r square gets cancelled. So what remains would be E is equal to, there is rho, there is r by 3 epsilon naught. So this is the field. So it's surprising here, because in this case for this region E is proportional to r. So from the center it is increasing proportionately. In terms of vector quantity, we can write E is equal to rho r by 3 epsilon naught into n cap. It is normal to that small region. This is what we get. Now suppose if r is equal to 0, that would mean it is center of the charged sphere. Center of sphere. So in this case, even E is equal to 0. So we find that the electric field is increasing as seen here, and then it becomes a constant and decreases. So if you plot this as a graph, if you're plotting the electric field with distance form of a graph, so we take distance here along the x-axis and field along the y in terms of magnitude, then somewhere here would be its radius. So the field is increasing as seen here. At some point here the field is maximum, and that value we saw what it is. So that is equal to 2 by 4 pi epsilon naught into 1 by r square. So what you find is r square. So the field is increasing. So up to this point it is increasing proportionally, because we have seen that E goes as r. So this is proportional to E is proportional to the distance, and then from here it goes as 1 by r square, so it falls off rapidly as 1 by r square. So this is the graph for reticle versus distance. Thank you.